Now it should be recorded. I will share my screen. And before I start to discuss about multiple regression, it is maybe quite nice to go back to our previous computation last time to only briefly repeat basic results and try to prepare a simple regression model which was trying to explain prices of the flats by its sizes. And due to discussion about impossible interpretation of original constant of intercept, we also decided to center our variable size of the flat. So we have created a variable which was called C size. So it was centered size of the flat. And by this procedure, our results were following. Intercept was nearly 900,000 Czech crowns, and it was estimate of the price for the flat which has average size. It was approximately 65 square meters. So the flat with 65 square meters price was approximately 900,000 Czech crowns. And the next coefficient, 14,300 approximately for C size, says that average price per 1 square meter was approximately 4,300. Or if you like to follow classical interpretation of slope in regression, it says that if the size of the flat is increasing by 1 square meter, its size is increasing approximately by 14,300 Czech crowns. So that's only a brief repetition. And the last figure, which I would like to repeat, was the explanatory power of this model, and R square was approximately 0.47, or in other words, 47% of prices were explained by the sizes of these flats. So that's our basic repetition of previous results. And today, our main task would be to add some more variables in our regression model and to explain maybe more from prices of flats. So it means we would like to achieve higher R square than 0.47. Last comment related to our data analysis is that for sizes of flats, we have filtered one big flat as this flat distorted our results. So that's why the biggest flat in my data file is filtered here. Here you can see filtering icon in chess environment. So that's only a brief repetition of previous results. And currently we can follow our presentation and we can briefly discuss about multiple linear regression from theoretical point of view, and then we would implement this theoretical knowledge into practical skills in chess environment. So I hope that pictures can help understanding statistical procedures a lot. So that's why we will start with a simple picture. And once again, this picture is copied from Andy Field textbook. And here we have three variables at once. One dependent variable, which is recording sales, so it means whether we are successful or not in selling our records. And here we have two independent variables. The first one, this axis, is number of plays on radio per 1 week from 0 up to 70. And the next independent variable, next axis, is about advertising budget, which is measured here in thousands of pounds. And here we can see not line as in simple regression, but we can see regression plane. So if we have 3 variables at once, we have 3-dimensional space. So the picture of my data, which is describing relationship between 2 independent variables and 1 dependent variables, is changing from line for regression analysis, which is linear, to plane. So plane is describing the shape of my data. And you can see that for this plane, nearly the same as for line, there is some intercept or constant. So it means where this vertical axis is intersected by this plane. So this is once again intercept or constant of my model. And as I have 1 and second independent variable, I need 1 and second slope. So first slope and second slope is following the first and second independent variable. So these are these 2 slopes for this case. So this is so-called multiple regression by picture. So I have at least 2 independent variables, and my problem is only slightly more complicated than previous one. I am not inspecting relationship between 1 and second variable, but I have 1 dependent variable and more independents. So maybe that my question can be, is more important for sales of my records to be played on radio or to advertise more? So this can be more advanced question for multiple regression. Before we start to solve similar questions for flats data examples, we would go slightly into some theoretical details behind multiple regression. So let's imagine that we have some set of independent variables. Usually we call independent variables in statistics as X. So that's why we are discussing about so-called X data matrix. So X data matrix means that I have more than 1 independent variable. For example, X1, X2, X3, X4, etc., etc. And you can see that technically these independent variables can be measured by some figures, such as X2, X4, but these variables can be also binary variables, such as yes, no, male, female. Only for technical reasons, usually in statistical packages such as JASP, SPSS, MPLUS, etc., it is not expected that you will be using these tags, but you would be using usually values such as 0 and 1. If you go back into my data file, you can see that for many variables, this property is followed. For example, whether the flat is new or not, 0s and 1s. Whether the flat is reconstructed or not, 0 and 1, etc., etc. Whether it has balcony or not, 0 and 1. So these are classical binary variables. And we should remember that our independent variable for classical regression models could be continuous, it means long scale, or another option is that we have also variables that are binary, so it means it usually follows 0s and 1. Another coding can be also applied, but 0 and 1 is the best one for interpretation. So once again, I recommend you use variables that are continuous and ideally centered, or use variables that are binary. So these are 2 best options for regression models for interpretation of results. So that's data matrix with independent variables, usually called by big letter X. We are starting with some formalization of regression models, so please remember that usually set of independent variables is called matrix X. if we are discussing about dependent variable, for example, in my case, dependent variable is this column with prices of flats, and one column is usually called in so-called matrix algebra, which is part of mathematics, as vector. So vector y is usually symbol for dependent variable. Y with small letter means this is this set, this first column in my data. So for example, here in my data, this is y vector, and these individual columns merged together are matrix of independent variables. So here I have vector of dependent variable, and here I have matrix of independent variables. So that's the description of my data in so-called matrix algebra terminology. And last one vector that I would like to get is vector called usually betas, which is vector of regression coefficients. I would like to get estimate of intercept. For population, the intercept is usually described as beta 0. So beta 0 is the level of dependent variable if independents are at 0 for the whole population. So that's the first part of so-called vector beta. Beta 1 is regression coefficient or slope for the first independent variable. Beta 2 for the second one, beta 3 for the third one, etc., etc. So this vector is including one part for the intercept and the rest part of for independent variables. For example, if I would add into my model C size as centered size, and I would add, for example, whether the flat is new, whether it is reconstructed, and whether it has or not balcony. So I would get 1, 2, 3, 4, beta 1, beta 2, beta 3, beta 4, and intercept. So the vector beta would have 5 pieces of information. So that's how we can, in mathematics, describe our regression model. I would skip this matrix algebra description for a minute, and I would use only a simple description by classical equations. So, basic idea for regression is that my model for population is following this equation. So if I would have all data for the whole population, I could prepare model for dependent variable, and this value would be based on some average value, which is hidden in constant or intercept, plus impact of the first variable. It means the first slope multiplied by the first variable called x1. Then impact of the second variable, beta 2 multiplied by x2. Then plus, 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 and the last one variable is usually in a regression equation called as a piece variable. That's why beta p multiplied by xp is the last part of the regression model. And this classical regression model for the population is also accompanied by the last part, which is usually using the Greek symbol epsilon. And this symbol means there is always something that is not explained by my regression model. So it means by this part. And there is still some random variation which cannot be explained by my set of independent variables. So this is random part, or sometimes it is called as error, random part, etc., etc. In regression modeling. So I have something what can be explained by this part, and I have also something that cannot be explained. That's a random error. If I am trying to estimate average for my dependent variable, I am preparing equation for EY. EY stands for expectation. So average for the population in statistics is usually called expectation. So I am computing expectation for dependent variable. And this average is based only on this part and is eliminating random error. So estimation of the average of dependent variable is based on classical regression equation. So I would take constant, add impact of the first variable, second variable, up to the piece variable. That's regression equation for the population. Unfortunately, in the most cases, I do not have population data, but I have only data from my sample. That's why I am not able to compute directly beta 0, beta 1, beta 2, but I can only compute something what I would call estimates. So these estimates are usually symbolically described as B0, B1, B2, BP. So instead of betas, symbols for population, for samples we are using small b's. So this is estimate, not real, but estimate of this parameter. It means intercept or constant of the population. This is the estimate of the impact of the first variable. This is the estimate of the impact of the second independent variable, and this is the estimate of the impact of the last one, piece independent variable. So currently, I do not have population data, I have only sample data, and that's why I'm computing only estimates of these coefficients. And as far as you know from previous discussion about regression, we try to go back, so it means from our estimate to the population values. So there are two strategies in classical statistics for this generalization from the sample to the population. First one is that we are performing some statistical tests, such as t-tests in regression analysis. Alternative strategy in classical statistics is using confidence intervals. So that's the style by which we are trying to infer our results from the sample, from our estimates, to the real population values. So that's only a brief insight. And now we would make quite a quick switch into matrix algebra description of these regression models. So maybe that next slide will show you very simple equation for regression, but maybe it will be very, very complicated for you for the first insight. Once again, I would like to repeat that X is a description of matrix, so it means sets of columns for independent variables. Y is description of dependent variable column, and beta is a set of individual intercept and regression coefficients. And if I would take all these together, I can type following very simple formula. So instead of this quite long formula, I can write it very simply only by this way. Y dependent variable is based on multiplication of individual coefficients, betas, and matrix of independent variable plus vector of random errors. So these are vectors. This is vector, that's vector, and that's also vector, and this is matrix. So this is how it works very easily if you would like to avoid such complicated equations as this one. And it can be proven, I hope very easily, but I don't know how efficient you are in complicated mathematics, that if you try to compute these estimates, such as constant, first slope, second slope, etc., you can use following formula. So you can take your original matrix of independent variable and transpose it. transpose means that I would take these columns such as new, reconstruction, whether balcony is yes or no, and C size, and I would replace these columns by rows. So transposition is exchange of rows and columns. So that's why we discuss about transposing. So this matrix is transposed and multiplied by original data matrix of independent variables. So that's the first part of this equation, how a JESP or another package would compute results by ordinary least squares techniques. Then, if you multiply these two matrices, you would make something what is called inversion in matrix algebra. You know that if you make the first power minus in classical mathematics, you would take 1 divided by this value. In matrix algebra, it is slightly more complicated. If you take inversion, it means that you try to find a matrix by which you multiply this matrix and you would get matrix with only units. So that's quite a more complicated step. And then these inverted matrix, you once again multiply by original matrix of independent variables, once again transposed. And the last part, you multiply all this stuff by vector of dependent variables. So this is, let's call it, very simple formula how you can directly from your matrix of independent variables and from your dependent variable vector compute estimates. This is how it works in software. So by this formula, software will find a solution. If you are not familiar with these computations, here are some recommendations that you can find some description of this slightly advanced mathematics. Math is fun, Khan Academy, about multiplying matrices. So let's go to these pages if you are interested more into the explanation. Why is it so that estimates of regression, intercepts and slopes can be found by this expression. So if we go back in JESP, and that's our main intention, so we would find once again some basic result such as R square, such as individual coefficients, so it means intercept and slopes, and individual tests, individual confidence intervals, etc., etc. So now we would switch into JESP and we would compute our results. And I would first of all discuss about possible independent variables that we can use for this first multiple regression example. So previous example was only price dependent on C size. And currently, we would add some more independent variables. So my recommendation is that we would add also whether the flat is new or not, whether the flat is reconstructed or not, and I would, for this first insight, add also the variable whether the flat has balcony or not. And before we start any computation, I would ask you to help me, and we would briefly discuss about possible results. So the first question is, what is expected result if the flat is new or not? Would new flat will have positive or negative effect on price? So what's your expectation? Positive effect of new flat on price or not?
A positive relationship.
Okay, so we would expect that slope or regression coefficient for new would be positive value. So it means that newer flat would be maybe more expensive. Okay, that's the first expectation. Second one, whether the flat is reconstructed or not. So it means whether there were some changes and some modernization in the flat. So once again, is your expectation that these modernization processes can increase the price of the flat or not?
Increase.
Sorry, increase?
Yes.
Okay, thanks a lot. And the last one question is related whether it has balcony or not. So whether flat with balcony can have on average higher prices or not, or whether it has no impact.
Also positive, it has impact.
Okay, so before we start, we are expecting from previous analysis, a positive effect of size. So we didn't discuss about it. We know it from previous analysis. And we are also expecting positive coefficient for new, reconstruction, and balcony. Only before we start computation, there is one technical necessity in JASP, at least in your versions. In previous versions, I guess it wouldn't be necessary. If you like to enter independent variable into regression procedure, it should be defined as a variable which is cardinal. So it means variable with this scale. So I would click here into new and change scale. I would click here into reconstruction and change scale. And I would click also here balcony as and change scale. And now all variables dependent as well as all independents has definition that it is the scale. So that's only a technical necessity for JASP. And I would go back. So first of all, we would need to add one more regression analysis. So I would click into regression, linear regression from classical part. And I would define variables. Before I start, I would only describe my analysis. So I would call it that I am here applying multiple regression with size, new, reconstruction, and balcony. So that's enough to type. And let's start definition. So first, the variable which I would like to implement is dependent variable. So it means price of the flat. And let's use independence. So C size is the first covariate. Then whether it is new or not. Then whether it is reconstructed or not. And whether it has balcony or not. So these are four independents. So now JASP is recomputing our model. And before we will start to read results, I would also visit statistics option. And please ask also for confidence intervals here and use default 95%. So that's all results we would need for the first insight into a regression model. All the rest we can leave as it is. And we would start discussion about results. So currently, you should find the same results as I have here. Once again, I would like to repeat that the biggest flat in our data file is omitted from data analysis. And before I start to read results, maybe it would be nice to compare my current model. So it means model which is including centered size, whether it is new or not, reconstruction and balcony and yes or no, with the previous model. And previous model included only C size variable. As it would be quite impractical to see these results and every time go up and find results for previous model, there is one quite nice option in JASP. And you can ask directly for this model to compare our current model with previous model, which is including only C size. Let's see how it works. So I would click once again into the dialog for input. I would go into model option. And here on the right-hand side, I can choose one or more independent variables that can be added to so-called null model. So model that can be compared to our current model. So if I click here, JASP is recomputing once again our results. And here we have the first row, which is called H null. And this is the result for previous model with C size only. I can see also here original model for C size only, and then H1 every time currently means this is our model including more than size of the flat. So now I can make, for example, comparison of explanatory power of original model, which was simple regression, and multiple regression with 3 more variables. So originally, I was able to explain approximately 47%. Currently, the increase is not a very big one. I'm currently possible to explain approximately 51%. So I added 3 more variables, but the result is not so impressive. So maybe that our previous model was not quite poor, but was quite good in comparison with our current model, including 3 more variables. So that's the first comparison. Second table we didn't discuss last time, and I promised we would discuss today, is so-called Anova table. So if we have more than 1 independent variable, so this is this section called H1, so it means second part of this table, I am computing something what is called overall F-test or Anova test for regression analysis. So now let's go briefly into details of this test. Null hypothesis for this test says, okay, take all your independent variables, and null hypothesis says that no of these independents influence dependent variable. It means it says that size of the flat, whether it is new or not, whether it is reconstructed or not, whether it has balcony or not, no one of these variables influence price. So that's the null hypothesis for this so-called Anova or overall F-test. Alternative hypothesis says that at least one of these variables in the population has impact on dependent variable, it means on prices. And as you can see, this test is based on division of so-called sum of squares or mean squares into regression, explained, or residual unexplained variance. So these 2 sources of variances, sum of squares or mean squares, are computed separately. And based on these mean squares and their division, so it means this value 5.801 multiplied by 10 power 12 power divided by this value gives you this ratio. So this test statistics for this Anova or overall F-test is based on a ratio of these 2 values. And here is the evaluation. Once again, null hypothesis says no independent variable influence dependent, and alternative is at least one independent variable influences dependent variable. This p-value is quite low one, 0.000, many zeros, and 39th place after decimal place is the value 8. So now I would be happy if somebody can help me to make conclusion about this test, whether I would reject null hypothesis or whether I wouldn't reject null hypothesis. So what could be a correct conclusion here for this overall F-test?
We should reject null hypothesis.
Yeah, p-value is very, very low one. So I would be happy and I can conclude that at least one of independents is influencing dependent variable. It's not a big surprise, I would say, but this is how it works. So usually if you are performing regression and if you are presenting regression by the article or presentation on conference, it is usually expected that you will also add results for this overall F-test, at least by this p-value. Okay, the most important part and that's where we are currently, is of course the table of so-called coefficients. So now we would discuss in detail about these coefficients. So this first part of table called H0 is the same result as we discussed last time. So that's not necessary to repeat, but we would go into this second part, which is called H1. So here is intercept, C-size, new, RICO, and balcony. And before we start to discuss individual coefficients, individual slopes, it would be good to discuss about the meaning of intercept for this new model. Previously, it means for this simple regression model, the meaning of the intercept was that it was estimation of the price of the flat with the average size. What could be the interpretation of the intercept in my current multiple regression model? What could be the interpretation of this approximately 830,000 Czech crowns? Can anybody help me?
That is the average price for flat, including all of the variables we added to it.
That's not precise.
No?
What does it mean, including?
That it's counting with all of these variables that we added to the model now.
Okay, so what
Not
is
only
this flat
with
about?
size.
Is average sized flat or small flat or big flat? It is newly built flat, reconstructed, with balcony or without?
Yes, it's counting with all of these together to make the average price. No? Okay, sorry.
That's not still correct. Some other options, some other opinions. So once again, let's go back to simple regression case. The meaning of the intercept was, it is estimate of price for the flat with C size at 0. So it means average flat according to its size. So what could be the interpretation of the intercept here? It is analogy.
It's a price for an average flat with that is not new, not reconstructed, and without balcony.
Yeah, that's great. Of course, as if we previously centered continuous variable and we are using the rest of variables that are binary, such as 0 and 1, the meaning of the intercept would be, it is the estimate in our current case of the price of the flat, which is according to all variables at 0. So it means average size, it is 0 for C size. Not new, as it is 0 for new. Not reconstructed, as it is 0 for RICO. And without balcony, as it is 0 for balcony S. Yeah, that's great. So that's the interpretation of the intercept. Once again, if we didn't previously centered C size, no such interpretation would be possible, and interpretation of intercept would be totally useless. So that's intercept. Okay, and now we would go further and we would discuss about C size, new, RICO, and balcony slopes that are available here. So first of all, C size. Originally, it was 14,300 approximately for simple regression. Currently, it is slightly lower. The reason is very simple. We added some new variables that somehow usually changed previous coefficients, but still it seems that it is a very important variable. We will discuss about its importance in a few minutes. So still the interpretation is that the average price for the square meter is approximately 13,500 Czech crowns. But now slightly small change in the interpretation if we take also into account whether the flat is new, reconstructed, or whether it has balcony or not. So this coefficient is sometimes called as partial coefficient, as we are including new reconstruction and balcony into our model, and we are fixing, controlling these effects. So this was uncontrolled effect. Here we have effect under control. So whether it is new, reconstructed, or whether it has balcony or not, is under control. So it is so-called partial regression slope. So next one is new variable and slope for new variable, and it says that the value is approximately 500 of thousands. So now it would be good once again to add interpretation. What does it mean? So it says that if the flat is new, if I control the size, so it means for the same size, whether it is reconstructed or not, and whether it has balcony or not, so the price is increased by 500,000 Czech crowns. So it means if the average sized flat without balcony, not reconstructed, and old flat is for approximately 830,000 Czech crowns. So the new flat with the same property, but only if it is new, is approximately about 500,000 more expensive. So that's the interpretation of this coefficient nu. So this variable is binary, only 0 and 1. So its value for this coefficient says what is the price for new flat in comparison with old flat. Next one is the slope for reconstruction. So it is approximately 70,000, and I hope that somebody can help me to interpret this result. So please, if you can, what would be the interpretation of this 70,000?
So if it's reconstructed, then it's approximately 70,000 more expensive than not reconstructed.
Yeah. If I control the size, if I control whether it has balcony or not. Only one more information I should add, the flat could be new or could be reconstructed. A combination of both of these is not possible. Real data. Okay. And last one is whether it has balcony or yes. The value is slightly bigger than for reconstruction. If somebody else can help us to interpret this value.
That if a flat has a balcony, then it adds to the total value 76,000.
Okay. So once again, if I control the size of the flat, whether it is new or not, whether it is reconstructed, so balcony add something like 77 approximately 1,000 Czech crowns. Okay, so that's interpretation of these coefficients. Before we would go further, it is necessary once again to repeat the important information that all these coefficients we have just interpreted are coefficients that are valid for my sample. Once again, if I go to the presentation, we have just computed this B0, B1, B2 up to BP. So these are estimates only, and these are estimates that are valid only for my sample. And I would like to generalize my results to the whole population. So that's why I would like to say, okay, these values are valid for my sample. What would be possible value for the whole population? And the easiest and maybe straightforward answer for these questions are offered in the last two columns that are called confidence intervals. So here it is, 95% confidence interval, lower and upper. And you can see here directly estimates of coefficients. So for example, for intercept, which is in my sample, 840,000 approximately, it can be 770,000 up to 880,000. So that's the estimate for the population. C size, or average price per square meter, approximately 13.5 thousand Czech crowns here for my sample. For the population estimate is 11.6 up to 15.3 thousand Czech crowns. For difference of new and old flat, approximately 500,000, it can be quarter and also maybe up to 750,000. So maybe that my estimation is quite unstable. The reason why this confidence interval is so long is maybe that there are only few new flats in my data. So that's the reason usually if I can see big confidence intervals, there can be two reasons behind. First one, small sample, and second one reason can be big variance in my data. And for reconstruction and whether it has balcony or yes, we can see quite strange result, as here, as it was expected by my discussion before data analysis, reconstruction and also presence of balcony has positive impact. But if I can see confidence interval, there is also some chance that the effect on price can be maybe negative, minus 5,000, minus 4,000, up to 150 approximately 1,000. These are confidence intervals. If you can see such result that the coefficient can be negative as well as positive, it means that we do not have some precise evidence to say that these two effects can be present in population. So maybe it's impossible to generalize results about impact of reconstruction and impact of presence of balcony to the whole population. Once again, the reason behind can be that there are only few flats reconstructed and maybe also few flats with balcony, or maybe there can be also other reasons. So that's confidence intervals. Usually, and maybe even more classical way for generalization of my result would be to read results of t-test and p-values. So it means these two columns. So if you can see for C size, the t-value is approximately 15. Once again, if the value of t is in the range of -2 to +2, the result would be in the range which is not rejecting null hypothesis. If it is outside of +2 and -2, then you would reject null hypothesis in classical testing. So for C size, as well as for nu, these t-values are outside of the range -2 and +2. And that's why I would call these results usually as statistically significant. I would also add a comment that current recommendations in the literature says that these expressions such as statistically significant and insignificant shouldn't be used, and it is only enough to say your p-value, and the reader can recognize itself whether he or she thinks that it is important or not. But still, according to classical statistical testing, size and whether the flat is new or not seems to have an impact. So I can generalize the impact of size and whether the flat is new to the whole population. That's the meaning of these p-values. So there is some option for generalization. But if you can see the effect of reconstruction and balcony, so these p-values are at least above conventional level and this classical alpha level by which we are comparing these p-values is usually 0.05. This is above this 0.05, and I can say, maybe it's a pity, but I'm not able to prove effect of reconstruction. I'm not able to prove effect of whether it has balcony or not. So maybe that these two effects are proven and these two are not proven at all. So that's all about p-values, t-tests, and so-called statistical significance and significance discussion. And maybe the last information, but also important information, is that we can compare the effects of individual variables. So to say whether a size is important than new, whether reconstruction is important more than balcony, etc., etc. If these variables do not follow the same scale and c-size do not follow the scale 0, 1, which is in new, reconstruction, and balcony, so we are not able to compare these so-called unstandardized coefficients. And instead of it, we need to go into this column, which is called standardized coefficients, or sometimes we call these as beta coefficients. Excuse me for this confusion, but beta coefficients in a regression are sometimes the expression for standardized coefficients, and sometimes, as far as we know, for coefficients for population. So these are two meanings of betas in a regression. So here we are discussing about standardized coefficients. And these coefficients can be directly compared in spite of the fact that these variables do not follow the same scale. So this value 0.645 says this is the most important variable as it is much bigger than the rest. The new is 0.15 approximately. So it seems it is approximately 4 times lower impact in comparison with c-size, but still 2 times higher effect than reconstruction and whether it has balcony or not. So that's about a new variable. And the last two variables, reconstruction and balcony, the effect is similar and very, very weak in comparison with previous variables. So maybe that the best strategy would be to omit these two variables. From substantive point of view, and also for statistical, from statistical point of view, these are nearly useless. So if we would exclude these two variables from my model, maybe that my model would be nearly the same quality. So it means that R square would be nearly the same value, and we would have a model which would be more simple. The ideal case in statistical modeling is usually to find model which is as simple as possible and as quality as possible. So if we combine these together, so I would here recommend to take only c-size and new as variables into my model. So here I would recompute my model. So I would take a copy of previous model. So plus icon. And I would take only brief description. So multiple regression with size and new only. And I would take reconstruction and balcony outside of my model. So here it is. And we can see results of my model. So R square slightly decreased from 0.51 to 0.5. But it is only a very, very small decrease. And my model is still quite good, and two variables, c-size and new, are implemented. The values of standardized coefficients are still close to previous one. So it says still that size is 4 times more important than new variable. So here we have recomputed results for my multiple regression case. So I would go through these results very quickly. And now, as the last step today, I will briefly discuss about inclusion of so-called dummy variables. Sometimes I can use variables that are not binary, that are not continuous, but they are ordinal scales. So for example, here I have the variable which is called city size. If I double click into this variable, I can recognize here that I have 4 options, 1, 2, 3, 4 for this variable. The meaning of these options are: 1 is the smallest villages, I guess up to the 2,000 inhabitants, and the 4 are the biggest cities in the area from which data were sampled. I guess these were cities up to the 100,000 inhabitants. So 1, 2, 3, 4 are codes for different sizes of villages and cities. And this variable, which is ordinal, you can see the scale here by this bar chart icon. So this variable shouldn't be directly implemented into regression model. But there is one way how we can handle this task, and that's inclusion of so-called dummy variables. So if you have nominal or ordinal variable with more than 2 categories, so it means it's impossible to code it only 0, 1, there is option to create set of so-called dummy variables. And the dummy variable means that I would take this original variable and I would prepare variables that are coded only as 0, 1, so these are binary variables. And here we have variables that are called size 2, size 3, and size 4. So it means that the second code, size 2, says whether this city size is true or not. So if I go down slightly, so I would try to find some case. Yeah, here, for example, city size was 2, and for size 2, there is 1 for these cases. For other, there are zeros. The same style is applied here for size 3. So if city size is 3, in size 3 is 1. For other cases, there are zeros. And the same style here is applied for city size 4. I would once again try to find some case. Yeah, here we have, for example, data for city size 4. And for size 4, there is code 1. For the rest, there is code 0. So here I prepared 3 new variables describing size 2, size 3, size 4 for original city sizes, and originally we included 4 categories. The rule for dummy variables is that if you try to apply these dummy variables into regression, you must omit 1 category. So number of dummy variables n is original number of categories minus 1. So if here in city size we have 4 categories, we need to define only 3 dummy variables. So I omitted the size 1. It means the cities or villages with the smallest number of inhabitants. This omitted category is usually called as reference category. So I need to omit 1 category for statistical reasons, and I need to remember this omitted category for interpretation of my results. So that's dummy variables. And here is also very simple recommendation. We would add 1 more recommendation in a few minutes. And simple recommendation is that if you try to omit 1 category, use category with the lowest level of dependent variable. So here, for example, I omitted the smallest villages, as I expected the price of the flat would be the lowest for villages with smallest number of inhabitants. So that's why I'm not here implementing variable size 1, and only size 2, size 3, size 4 are here. Once again, 1 of these categories I must omit, and I decided to omit category size 1, which is expected to have the lowest prices of flats. So here I have 3 new variables, and instead of this variable, which shouldn't be implemented into regression, I would implement these 3 dummy variables. So That's how it works. I would make once again copy of previous analysis, and I would add title. So I am now performing multiple regression with dummy variables. For simplicity, not to combine previous results and current results, I would recommend to take only C size as independent variable, and then size 2, size 3, and size 4. I guess it won't work currently as these variables are not defined as cardinal, so I will try. No, it doesn't work, so I need once again go back, click into size and define these variables size 2, size 3, size 4 as scale variables. So now it is defined correctly. So I would go back, size 2, size 3, size 4, and add to C size. So currently I have one variable measuring the size of the flat, and then variables measuring the size of the city or village, size 2, size 3, and size 4. Once again, I need to remember that one category from original variable city size is omitted, and it is variable which is describing the smallest villages up to 2,000 inhabitants. Okay, first one is a description of my current model. So I can see that R square is currently increased from previous 0.47 for C size only up to 0.72. So nearly 3/4 of differences of flat prices are currently explained. So it seems that the variable which is describing city size is really important for my description. So that's the first insight. I would skip results for Anova test. This is still the same or nearly the same, but I would go here into description of coefficients and then on t-test and confidence intervals. Before we start to describe size 2, size 3, size 4 coefficients, I would be happy if somebody can help me to say what is, according to his or her opinion, interpretation of current intercept, which is approximately 710,000 Czech crowns. So can anybody help me to interpret?
It's a price for average size flat in the category size 1, which means it's a price for flat in the smallest villages.
Yeah, that's great. That's correct. As it is the flat for which C size is at 0. So it means average size flat, and for which size 2, size 3, size 4 are all zeros. So it means it is not a flat in the city size 2, city size 3, city size 4. So it must be flat from city size 1, which is the smallest village up to 2,000 inhabitants. Yeah, that's great. So that's 700. I would skip interpretation of C size. This is still quite similar. And let's go to size 2, size 3, size 4. So if I know that I have omitted category number 1, it means smallest villages up to 2,000 inhabitants, this value 64,000 would tell me that for villages and cities that are slightly higher, I guess it was from 2,000 up to 5,000 inhabitants, the prices are slightly higher, approximately 64,000 higher on average. For size 3, it was, I guess, from 5,000 up to 20,000 inhabitants. In comparison, once again, with omitted category, it means the smallest villages, the increase of price is 96 or 97,000 more. And the biggest figure we can recognize for the last one. So it means it is comparing some big cities, I guess up to 100,000 inhabitants with omitted category, so it means small villages. So from substantive point of view, it seems that it really matters whether the flat is in big city or not, as these two coefficients are quite small one in comparison with this one. And if we go back to the rest of outputs, so it means confidence intervals or p-values, we can see that for size 2 and for size 3, the results according to p-values or according to confidence intervals are not convincing. So maybe that prices of the flats in second category of city sizes or third category of city sizes are not different from the smallest villages, as these p-values are quite big one, and also confidence intervals are from minus till plus. There are many reasons for this result, but maybe that substantively size 2 and size 3 of cities and villages have nearly the same prices as for the smallest villages. So maybe that these two variables differentiating second and third category from the first one are not necessary. So my last step, analytical step, would be maybe to change my original idea that I need to differentiate every category of the city size, and maybe that I need only to differentiate city size 4 from the rest. So my last analytical model we would perform and briefly interpret would be maybe something that I could make that I could discuss as simplification of this model. So I would enter only C size, and I would enter only the first category of city size, and the rest would be omitted. If I make such a change in my model, what would be omitted category if I add only size 4? What would be the rest for which I would be preparing comparisons?
Sorry, Professor, you were frozen for last 2 or 3 minutes.
Okay, sorry for that. Now you can hear me?
Yeah.
Okay,
yes.
So once again, what we are currently discussing is that this C size 2 and C size 3 coefficients, at least according to p-values or confidence intervals, are not convincing evidence that there are some differences for prices for second category and third category in comparison with the first one. So my proposal is that as the next model, last one today, we would omit these size 2 and size 3 variables, and we would perform regression analysis only with size 4 category. And let's go for it. So I will make a copy. So I would once again change the title. So multiple regression with only size 4. So here it is. So I would exclude size 2 and size 3. So now we have pre-computed our results. First of all, you can see that R square is nearly the same as for previous model, 0.718, and previously it was 0.721. So there is nearly no decrease in quality of the model. So still, explanatory power of the model is quite nice. And now we would like to interpret these results. So first of all, if somebody can help me with the interpretation of the intercept, it would be nice. So what is current interpretation of the intercept?
Currently, it's in price for an average flat in city size 1, 2, and 3 together.
Yeah, of course, which is of average size. Yeah, that's correct. So now the reference category are all cities and villages up to the, I guess, 50,000 inhabitants or something like this, which was category 1, 2, 3. Yeah, and the only category which I am now comparing with the rest is the biggest cities, 50 up to 100,000 inhabitants. And I can say that maybe for this first category, the prices are approximately 500,000 more expensive. I can also see that maybe in population this difference would be slightly small, 467,000, or slightly bigger, up to 600,000. So that's the estimation according to confidence interval. So this will be my final model. Both of these results are substantively and also statistically important, as confidence interval do not include zeros, p-values are quite small one. So this would be currently my final model. As this is nearly the end of today's lecture, I would only add a small comment to know what will be our next step during the next lecture. And our next step would be also to discuss whether we should implement only size for variable, which says, okay, all flats for the biggest cities are approximately 500,000 more expensive, or whether we should discuss about maybe more detailed interpretation that not only every flat doesn't matter which size it is approximately 500,000 more expensive, but maybe that the price per square meter can be different for big cities and small cities. So maybe we can somehow combine information whether the flat is in the biggest cities or not, and about the size. And this combination of these two variables we will discuss as a discussion about so-called interactions. So next time we will start with interactions of two variables, and we will learn how we can prepare such an interaction and how we can interpret results of such interaction, and we will find, I hope so, the best model for our data. So we would find the difference for price per square meter for flat in big cities and in small cities and villages. So that's all for today. So I would stop sharing, stop recording. Of course, if you have